you at least know the grade. All right, so number 78. If you had tried the rest of them, you probably got to this one. I was like, I don't know what the heck's happening. It says we have x to the third minus ax squared plus 11x plus 4. It leaves a remainder of negative 301. So I'm just going to say remainder negative 301. And we're dividing it by x plus 5. By x plus 5? Okay. Find a. Probably could have figured it out if you started it, but well, yeah, I'll go through stuff. I'm going to set up synthetic division. So synthetic division, we're dividing by x plus 5, so I'm going to put a negative 5. Did I not share my screen with you? Oh my gosh, every day. I knew when I was in the middle that I hadn't done it. Always yell at me as well. All right, so I'm setting up synthetic division. I'll put a negative 5 here. So I'm going to put the coefficients, right? 1, the coefficient of this is negative a, and then we have 11 and 4. And the only information that it tells us is the remainder is negative 301, so the remainder always goes here, right? So we know kind of what the heck do we do? You could work backwards, guys. Hey, if this is negative 301, 4 plus what equals negative 301?
Negative 305.
Yeah, negative 305. Like we're zagging backwards, right? We usually zig, we're gonna zag. Okay, work your way back. Usually we do this times this equals this. So if I want to work backwards, what would I do? Divide them. So negative 305 divided by negative 5.
61.
61. So this would have to be 50, right? Because 11 plus 50 equals 61. Work your way back. 50 divided by negative 5 to zag is negative 10. Now we don't have a value here, but we can kind of do it by just doing it this way. Bring down the 1. 1 times negative 5 is negative 5. Okay, so we're going to just focus on that. So you might have to do like a whole finagling, moving stuff around, maybe doing some stuff backwards. But we need to solve for a. So we would do negative a plus negative 5, or I'm just going to write minus 5, right? Minus 5 equals negative 10. So negative a is going to equal negative 5. So a is equal to 5. And that's, my friends, how you would do that. So there's one similar to that with 79. So try that one. Just kind of filling in what you can and trying to get it to a place where you can actually solve for a. Once again, the only one that we haven't got to yet is 80. It kind of goes with one of the theorems we talked about today. So instead of just like craftily explaining it to you now, I'll explain it to you tomorrow with the theorem and it will make more sense. So if 80 is not done when you pass it in, that is fine. So I will put something on Google Classroom today for that, but as long as you get it to me at some point tomorrow, you're fine. Any questions on that one or just with anything in general? Isn't that fabulous? So today we're kind of working through, I had some notes and then we found this. And like, is there anything worse than just like sitting and writing theorems? So I was like, we'll work off of this because they're all written for you. So it just gives us a few examples of some theorems we're talking about, the rational root theorem, the conjugate root theorem, and Descartes' rule of signs. How beautiful. So we have today and tomorrow, so we'll kind of look today, see how we're feeling, practice tomorrow, do our thing, go from there. So if you see anything that you need more help with, you let me know. Just as a reminder, I'll tell you tomorrow. Just as a reminder, I'm always after school if you need extra help. There's something else I was going to tell you about. So if you need extra help, I'll be after school today. I am here in person, obviously, and virtually. And just as a heads up, if I ever am just like not on, that's just because I'm here. I'm just like in my own little world. Just email me and be like, hey, where are you? I try to be on, but sometimes I get distracted easily. And I'm after on Thursdays as well. And if you ever need help on Wednesdays, I'm kind of just here chilling anyways, doing work, so I can always help you on Wednesday. But please never sit at home confused. That is just plain old silly. All right, so I'm looking at this 5 theorems about roots of polynomials, and we're just going to focus on the first one. So I'm just going to read it first. The rational root theorem. Oh, this sounds fun. Any polynomial function with integer coefficients, okay, so with basically if the numbers in front are just integers, just off the number line, of the form, and it gives a big old form, it just means it's a polynomial, so it's just the way of writing it, has a limited number of possible roots. So basically what it's saying, if I throw a polynomial at you, there's only a certain number of things that is actually a root of it. Not everything's a root of it, that would be kind of crazy. So it has a certain number of roots, where p of x equals 0. Oh, that means that the remainder is 0 if you divided it, aka it's root. So integer roots must be factors of constant terms. Rational roots must have reduced. Okay, this is why I hate theorems. Like, what is even going on? Blah, 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 blah. I'm just going to explain it to you with the actual math, because I think it makes more sense that way. So we have those other roots. We'll go back to those in a second. Can you just skip down to where it says finding rational roots? All possible rational roots occur in the form of an organized list. So I will show you how to do it. And then it says P over Q, we'll fill in next to that. And then we'll actually look at the example. Once again, all the words, too many words, it's math. Let's just get down to the math part. So in that kind of center box here, it says P over Q. And what that means, it's just a fancy way, I don't even know why they use P and Q. We are going to find the factors of the constant term. And this is going to look semi-familiar from what we've done with factoring, right? And we're going to divide it by the factors of the leading coefficient. Once again, that means a whole lot of nothing. Let's actually see what it means with a problem. But in the future, you will, I'll say a lot, constant over coefficient. That's what we're looking for. Yes. Constant over coefficient. That's how we are going to find the factors. So example 1. What are the rational roots of, should have written that higher there, 2x cubed minus x squared minus 27x plus 36 equals 0. If you think back to factoring like a trinomial, we usually kind of focus on the first and the last term, right? I know this has too many terms for us, but we kind of find the factors and then we see what works. It's kind of the same idea, okay? So what we're going to do, it says right below, we're going to find the factors of the constant. The constant is just a regular old number. So this is my constant. I'm going to warn you in advance. These aren't necessarily the hardest. It's sometimes you just have to write a lot, so just bear with me. And they made this the most annoying number with 36, so we'll go with it. Literally, you write out the factors of 36. So when we think like, 1, 2, 3, 4, but when you write them, you have to write plus or minus 1, plus or minus 2. 3 is divisible by 30, or 36 is divisible by 3, I should say. It's divisible by 4, not 5. It's divisible by 6, not 7, not 8. It's divisible by 9. Once again, I said 36 is like the most annoying number to start with. A lot of them won't have this many factors. 10, 11, 12. 9, yeah, 12. I'm just thinking what's divisible by that. 18 and 36. Woo, that's a lot of options. Now, lucky for us, we don't have to do the extra steps on this one. We're just doing a bunch of listing. Okay. Then it asks, what are the factors of the coefficient? Or I should say of the leading coefficient. I don't think it says that there, and it always annoys me. It should say of leading coefficient, because technically they all have coefficients. So this is my leading coefficient. So all those other things I don't actually really care about, which is kind of nice. They made this one not as torturous because it's just a 2. So you would write the factors of 2 are plus or minus 1 and plus or minus 2. Okay, so we have 2 big old lists. Now this is where this comes in. To find the possible rational roots, you have to divide the factors of the constant divided by the factors of the coefficient. So ready? Just kind of like doing a pattern here. So what do they say? Possible factors. So basically what we're doing, that's why I always write constant and then coefficient, because we want to do this over this, this over this, blah, 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 blah. So here's what I do. 1 over 1 is 1. I always do the over 1s first. 2 over 1 is 2. Oh, I can't say right. 3 over 1 is 3. Always with the plus or minus. 4 over 1, you can see I'm just kind of writing my original list here. Then that's plus or minus 6. And then 9 over 1 is plus or minus 9. And then 12 over 1, once again, why did we choose 36? And then plus or minus 18. And then plus or minus 36. But we still have more options. Because what we can do is we can take all of these constant factors and we can divide them by 2. So let's go through. You could get 1 over 2, because you'll see what happens, so there aren't as an aggressive amount. And then as I go, 2 over 2 is just 1. I don't need to write it again. So since 2 over 2 is 1, we're good. 3 over 2, okay, I need to write that. 4 over 2 is 2, we're all set. 6 over 2 is 3, we're all set. 9 over 2, that'll be a fraction. I'm like going crazy here. 12 over 2 is 6, 18 over 2 is 9, 36 over 2 is 18. Or 18, yeah, there we go. And that, my friends, are all of the possible factors of that thing. Now, they are not all factors. That would be crazy if something had that many factors, right? We could technically only have 3 factors because it's a cubic. But those are possible factors. So you guys are going to be, well, the next one isn't as bad because there's not as many options. So the one, when we flip the page in a second, we're going to kind of do the same process just to get used to that. This is actually the rational root theorem. It's like one of the most important ones. You're going to see it again. And then we're going to say, well, like now that we have this whole list, which ones are actually factors? Ooh, this is so exciting. I'm not going to torture you because that's just a lot. But I'll show you an easy way to check in a few minutes. So I'll leave that up for a second just because that was a lot. The second I started doing this, I'm like, 36? Really? That's just annoying. But sometimes we get really annoying. That's our life here. All right, so I'm just giving people a second if you're still writing. So I'm just going to flip to the back and we can kind of look. So now we're going to actually use the rational root theorem, not just find which ones could be, but we actually want to use it to find the actual factors. So what we're going to do is do our same thing, our list for our constant, our list for our leading coefficient, find the possible factors by doing constant over coefficient. There won't be as many options in the next one, so that will be nice. And then from there, we're going to say well, which ones are actually factors, and I'll show you how to check that. So having a calculator is going to be a very big use to you, because you're going to see why in a second. And then the second part will be all stuff that we've done, so it shouldn't be too bad. So I'm flipping to the back where it said using the rational root theorem. All right. So this one won't be as terrible with a number of things going on because we have 2x cubed plus x squared minus 7x minus 6 equals 0. So those factors are looking a little bit more manageable. So if it ever says something like use the rational root theorem to find, the roots or whatever, we always start with our lists. So we start with our constant. I'm getting lazy because I don't want to write the whole thing. So we're finding factors of the constant. So I just focus on 6. And I say, well, what are the factors of 6? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So a way more manageable list compared to that last one. And then once I have that, I'm going to do a list of the factors of the leading coefficient, which is right here. And that's not too bad because it's just plus or minus 1 and plus or minus 2. And the reason we do that is to figure out what are the possible factors of this polynomial. So once again, if it says what's a factor and you have no clue, you don't want to just go in blind, like who knows if anything's divisible by. So just as a remember, constant over coefficient. That's how we find it. So basically I just take each of these and I divide them by 1. So that will give me plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And then I take each of these and I divide them by 2. 1 over 2 is a half. 2 over 2 is 1, so we don't need to write it again. 3 over 2. And then 6 over 2 is 3. Okay, so definitely a nicer list going on here. So these are our possible factors. Oh gosh, now we're going to add a step. You have to find a factor. You're probably saying, are you like, how? Because I have 1, 2, 3, 4, 5, 6, but then they all are both plus minus. So technically we have 12 options. And I need to figure out what the heck it is. So this is where your calculator is going to be your friend. So take it out. Hey guys, we talked about remainder theorem when we were doing synthetic division. And we said if you synthetically divide and you get a remainder of 0, then that means that whatever that is the root. But we also said when you really do remainder theorem, if I say something like what's P of 1, like literally you could just take that and plug it in. I don't want to sit here and synthetically divide all day. That will just drive you crazy. So let's just I just kind of go in order. Is 1, 2, and then I'll do the negatives after. Is this a factor? So what you could do is take your original equation, and I do this all in my calculator. I'm going to plug 1 in to my equation. Okay. If the answer is 0, it's a factor. If it's not 0, it's not a factor. Okay, I have no clue if it's a factor, so let me throw it in. 2 times 1 cubed plus 1 squared minus 7 times 1 minus 6. And I did something wrong. I just got an error. Oh, what did I just do there? Squared. So I got negative 10. So we would say not a factor. Okay, it needs to be 0. So I'm just going to go to I don't feel like doing the negatives. I'm just going to go to 2. Once again, I'm just going to put this one in my calculator. And a lot of times in your calculator, like I can hit second. If I hit second enter, it's called entry. It just gives me what I put in, and I can just throw 2s in instead of 1s. So see in your calculator, if that's possible, or I can look at yours for you.
To do what?
If I hit second,
Yeah.
it's called entry, so it's second enter. It just pops up what I just put in, and then I can just throw 2s where I put 1s.
Oh, yeah.
Just makes life easier. Oh, lucky guess, that equals 0. Which means 2 is a factor of the polynomial. Okay, so you're always looking for that 0. Could you sit there and synthetically divide everything? Yeah, but who really wants to do that when there's no one in sight? Not me, I can tell you that much. So once you know a factor, now we can do synthetic division because we know for a fact that is a factor. So I'm going to do synthetic division using that root of 2. I'm going to take my original coefficients. And I'm going to do a little division here. So what do I get? 2, that's 4, that's 5, that's 10, that's 3, that's 6. I love synthetic division. Once you get it, it's just so quick. And what this does is it gives me a nice little quadratic trinomial, which I can factor. And then once I factor it, I can solve it. And then once I solve it, I have all my roots. So what does this factor to? 2x plus 3, x plus 1. Yeah, because 3 and 5. So when it says, what are the rational roots of blah, 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 we would say the roots are, I'm doing a little curly bracket, you can do whatever. I know 2 is 1. So on that last notebook quiz, I think it was the very last question, it says, what are all the factors? And then a lot of people didn't put the original factor given to you, which was 8. Like, you need to list all of them, guys. Even if you find something in the middle, or if it's given at the beginning, it's still a factor, it's still a root. So 2 is 1. We found that before. And then when I solve this, negative 3 over 2, and, oops, I could write today, and negative 1. So I got those from here. So all that work, I mean, it's actually, I like this weird thing. I like doing this part. I don't know. Writing lists like brings me joy, I think. I'm a list maker. So I like writing my little lists. But then it is kind of annoying once you have a lot of the options. So once again, don't sit there and divide everything. Use that remainder theorem. Just plug each of them in. Find when you get a 0. And then once you get a 0, then you can use synthetic division. But I will leave that up for a moment. I know it's always, especially when you're at home, it's always a little harder to keep up. So here's my question, because it doesn't matter to me, because we have today and tomorrow. We have 2 other theorems. They're not as much work, okay? This one, like, there's a few steps to it, I feel you. We have the conjugate root theorem, which is kind of a quick one. I just tell you something, basically, and you switch something. And then Descartes' rule of signs, you just literally look at signs, whether things are positive or negative. Would you rather try another rational root one while it's kind of fresh in our head? And kind of probably end on that because they take a few minutes. Or would you rather just get all the theorems over with today and then tomorrow practice all of them? So your option is another rational root one or new stuff. Does anyone have an opinion? Yes.
New stuff?
Okay. You're the only one saying new stuff. Okay, I'm gonna go with new stuff, and the other stuff isn't as bad. It's not as like working. New stuff in practice, perfect. We all agree. I just like that. So what's nice is tomorrow we have like a practice day, so it's not like we're just like killing ourselves and then we'll never see this again. We can try a few more of these tomorrow. Actually, a few of the problems, like we'll bring all of the theorems together. Okay, so a bunch of lists, check which one makes sense, go from there. So I was just getting used to that process here, but we'll do more of that tomorrow. All right, so I'm not writing the theorems out because they're just annoying to write theorems, but it's listed on the front of here. The conjugate root theorem. If a polynomial has rational coefficients in irrational roots, aka if the root is a radical, like a square root, or if you have an I. So this is what this kind of relates to. If you have a square root that has a radical in it or has an I in it, they occur in what we call conjugate pairs. So all that means, and this isn't necessarily on here, I'm just going to show you. If I say something has a root at 2i, does anyone know what the conjugate means? A conjugate just means if I have 2i, then I automatically have another root at negative 2i. So if there's one at 2i, there's automatically one at negative 2i. If there's one at 27i, there's automatically one at negative 27i. If there's a root at negative root 3. So these are both, so we're talking about irrational numbers here. Then there's also another root at root 3. So basically, anytime you see an I, if you have a positive, you also have a negative, vice versa. If you have a negative, you have a positive. So they come in pairs, basically is the main thing. And if you have a radical, same thing. If you have a negative, you have the positive, that goes with it. Or if you have the positive, you have the negative. So it's really nothing crazy. And you're going to see the actual problem, you're going to be like, oh, that's kind of easy. Because it just basically asks you, if I give you one of these, what's the other one? So once again, we call those conjugates pairs. Basically, it's the same term, just with the sign changed. But that's what happens when you are talking about irrational roots. I can't even talk, which is our square roots. And also with those imaginary numbers. So literally, on the back when it says using the conjugate root theorem, this is example 3. It says, a cubic polynomial has real coefficients. 2 of the roots are x equals 4, and x equals root 5. What is the other root? Okay. Well, x equals 4 is fine. That's just a regular root. But anytime you see a radical, if you have the positive, then that means the other is the negative, and that would be your answer. So this comes in conjugate pairs. If you have the positive, that means the negative of that same term is also going to be a root. Okay, that's it. That's all you have to do for example 3. I always like those ones.
Because 4 is a regular number.
Because 4 is just a regular number. It only deals with radicals, so square roots, in imaginary numbers that you have to do the pairs. And then for example 4 is kind of the same idea. We have a quintic polynomial has real coefficients. We have zeros at x equals 2i, x equals negative 3 plus root 5, and x equals 1. Name the other zeros. So what I usually do is just go, oh, I see an I. So since that's positive, I'm going to have negative 2i. So that one's, I have to add that one in. Yep.
Since the 5, it's just in another equation, you don't have to do the opposite.
What, this one?
Yeah.
So you do the number in between them. So it's just the sign that's right before the radical you would have to change. So this would change to x equals negative 3 minus root 5.
Oh, I thought you already changed it. Sorry.
No, it's it just has a real and I can't talk today. It has 2 parts, but that's fine. It can have 2 parts. That's not a big deal. Just whatever is directly in front of the radical, that's the one that changes. So the negative 3 doesn't change. And then once again, the 1's just a regular 1. You just keep it. And that makes sense because if I say quintic, that means it's a 5th degree polynomial, and 5th degree polynomial should have 5 roots. They gave us 3 of them, but since these ones have conjugate pairs, that added the other 2. All right, so then example 5. Example 5, that's kind of on the next page. It says find a cubic polynomial with roots, if I could write at negative 2i and negative 5. So here's how you kind of organize yourself. When I see negative 2i, I automatically also add 2i. So I have a root here, and a root here. Once again, if it's just a negative 5, you just keep it as negative 5. Now it says we need to actually find the polynomial this time. It doesn't just ask like where the zeros are. So what we need to do is write it in factored form. If I have a root at negative 2i, we would write that as x plus 2i. Right? If I have a root at 2i, we would write that as x minus 2i. And at negative 5 would be x plus 5. So we have a lot of experience with that. Those on our quiz. Don't get freaked out because there's I's. They do the same thing. We do have to do a little distributing. So pick two. I'm going to pick these first two terms. Our first two binomials. Distribute them. I'll get x squared. So then what happens is kind of magical, is you'll get minus 2i plus 2i, and those would cancel. So I don't even need to write those middle terms. And then last but not least, I would get minus 4i squared. Hey everyone, when I see I squared, what do I replace it with? -1. So if I have -4 times -1, this just becomes +4. So just little things we remind ourselves of from the good old past here. So once again, with that distributing, that's going to happen. And that's kind of the point. When you have the conjugates, when you distribute, the middle term will cancel out. And then you'll get something with I squared. So you don't actually have an I in your polynomial. It's just when you solved it, you would. So now let's distribute. X cubed plus 5x squared plus 4x plus 20 would be your final polynomial. So I feel like sometimes you're like, oh, but shouldn't we have i's? No. That just means when we solved it, we would have imaginary
Because
answers.
it was -I squared, it was 1.
Anytime you have I squared, it's -1.
Okay.
So in that case, it ended up being -4i squared, so that's where the +4 came from, the negative and the negative. So don't get freaked out when you're throwing i's in, perfectly fine. Put them in. Just remember, once again, we say they come in conjugate pairs. If you got a positive, then the negative goes with it, and vice versa. If you have a negative, you have a positive. But that's really the craziest that gets. So a lot of times, and that's one of the things that popped up in that was the last problem in your problem set. It was asking you to divide by like 4i or something. But if you divide by 4i, you also have to divide by -4i. And that would have been confusing. So we'll do that tomorrow to finish up. What do we have, 5 minutes? Do I want to do this? I don't think I want to confuse you with this rule, this next one. Not that it's confusing, it's just I only have 5 minutes and I don't. So we do have one last rule, Descartes' rule of signs. Basically, we're literally just going to list the signs out, whether things are positive and negative, and then we're just going to see how many changes there are. I'll explain that one to you tomorrow. One of those ones. I could rush it right now, but then I'll probably just confuse myself as well. So when we come in tomorrow, you are going to, we'll finish up number 80, I think it is, in the problem set. So if you want to submit it before that, that's fine, if 80 is not on there. We will kind of finish this up. The Descartes rule of signs will be quick, but once again, I just don't feel like rushing myself. There's another one on there. And then there's a few other things we will start to wrap up and just practice with these 3 beautiful theorems we got. And then just as a heads up, like you should hopefully be done with your other problems. I did throw another one out. Tons of fun. And I'm sorry, because some of these are just, you're just gonna have to do the work on a separate sheet of paper. It's not like you don't have room, which just drives me nuts, but I did not have time to edit it. Just as a heads up, numbers 1 through 9 in this problem set, which should be pretty quick. With rational, oh, that one's easy. That one's easy. That's just listing possible roots. That one's just really good. So that shouldn't be 9. 1 through 9. I'm gonna have to do Wednesday, but I'll let you work on it Wednesday afternoon. But just if you're, if you're sitting and you're bored, you have nothing to do. I'm sure you have things you'd rather do than math, but if you look in the problem set 1 through 9, if you want to kind of start getting boards, but that will be one for Wednesday. So it'll be if you all go over with you in the morning, and then I'll just say you can, then you can do that then. I'm gonna be a little bit high, but that's okay. That's okay. That's it. Let me pause.